Consider different types of waves, such as water waves, sound waves, and light waves. Which could be done to increase the speed of any one of these? So consider the choices below. Let's see what our choice is. If we change the size of the wave, how could we increase the speed? Changing. Mm-hmm. Increase the amplitude, that would
make it bigger.
That would increase the speed? Okay. That's what you think? But we want to increase the speed. It says, what could be done to increase the speed? So what could you do with the speed, the size? What could you do with the frequency?
Make it higher.
Increase the frequency? You're saying? What about the material that the wave is traveling through?
Vacuums won't work.
Some waves can get through the vacuum. Light waves get through the vacuum, but not sound waves. Oops. So a wave is a disturbance that propagates. Propagates just moves down. It keeps moving through a medium, and that's the substance that it is moving through, and that can be air, water, be earth, whatever it would be. Apply each word to a wave created when a child jumps into the pool. So what would be the disturbance? Child on the surface of the water. The water is the medium, okay. And how do you see that it's propagating? The ripples go out from the child, right? Mechanical waves require a medium. And electromagnetic waves can travel through a vacuum. So sound would be which? Sound would be a mechanical or electromagnetic? Mechanical wave, right. Because sound cannot travel through a vacuum. It needs a medium. It needs air molecules to travel.
Sure.
Okay, the wave shown is a pulse wave. And then we have periodic waves. So, oops. Let me get... I need a volunteer. Ooh, Caitlin's hand was up first. Okay, come hold one end.
Yes. That's her beat.
Someone messed it up. Previous. No. Okay, so you hold yours still. So a pulse wave. I need a new volunteer. She can't follow the instructions. Pulse wave would just be one going back and forth. That's a pulse wave.
Whoa.
Okay. So you have one disturbance. Go back and forth. Okay. Periodic wave is repeated disturbance. So this would be a periodic wave. And we're going to call those standing waves. It's called a standing wave, and we'll talk more about standing waves tomorrow. What moves? Nothing really is. It's just moving up and down. The medium is moving up and down. Well, there's longitudinal and there's transverse waves. We'll look. No. Pulse wave? Like dropping a rock in the water and seeing you'll just have one ripple go out. Right? If you dropped one rock, you just have one ripple because there's just one disturbance, right?
But there's multiple. Well, that's from the water coming up.
Right, from just the rock.
Because of the water moving. No, because the water comes back down. Yeah. When you send the rock, the water gets out way there. Get up the wave.
Okay, let's let's see. They might have the difference between. Okay, thank you.
Everything is relative.
Okay, so if a wave begins with a disturbance that is in simple harmonic motion, just like that standing wave, the periodic wave that I showed you, it would be in simple harmonic motion because it's a repeating oscillation at a specific frequency. The wave would then be considered a sine wave. And so if the wave in the diagram is moving to the right, in which direction is the red dot moving in each case? Does it move along the rope? No, so it stays in the same spot. It moves up and down. So think about like if you have a little floating boat in the water, like a toy boat, and then you make a ripple, does the boat actually, not a wave, like not like a crashing wave pushing it, but if you just had a little ripple, does the boat actually move? No, so the water is actually not moving. It's just moving up and down. Right? Not a crashing wave at the surf, not surf, but a wave. Yeah. Like the ripples that go out from something, the water's just moving up and down. Or think about okay, think about you're sitting in the wave pool and you're way down where you're close to the wall though, not up by the shore where the water's crashing, okay? If you're sitting on an inner tube, you just start moving up and down, right? Yeah. You don't move with the wave. Your waves are just going here. Okay. Where did I just put my pen? There it is. Okay, so these are transverse waves. What we just showed is transverse waves, where the particles move perpendicular to the direction the wave is traveling. So the wave was moving down the spring, but the spring was actually moving up and down. That point in the spring, okay? That's transverse wave.
Just like one point on the string, which is moving up and down.
Yeah.
The wave.
Yes. And so we can have the wavelength and amplitude there. And there are also what's called, oops, never mind, we're going to watch this first.
Transverse waves cause the particles of a medium to move in a direction perpendicular to the direction in which the wave is traveling. For example, a wave moving horizontally through a rope causes the rope and anything attached to it to move up and down as the wave passes through the rope. Transverse waves cause the particles of a medium to move in a direction perpendicular to the direction in which the wave
It stays,
is traveling.
you can't see the line very well, but there's a line that's drawn right here, and that it doesn't move off the line.
To move up and down as the wave passes through the rope.
It does. It looks like a drop of blood. Okay, a longitudinal wave, a wave in which particles move parallel to the direction the wave is traveling. I need another volunteer. A different volunteer. No one else wants to volunteer?
Oh gosh, good luck, Alex.
Let me find my other spring. I don't know if this one will work. Where is... Well, we'll use this one. Okay,
Alright.
you hold one end.
Alright, do I move?
Nope,
Alright.
let's not stretch it too far. So this would be a longitudinal wave, where one part is compressed. Okay, you see how there's a compression that moves along back and forth.
So pulse it goes up, though.
Yeah, no, this is still a pulse. This is still a pulse wave.
It's just longitudinal, not transverse. This transverse goes up and down.
That transverse is side to side.
This would be transverse. This is transverse. This could be transverse, however, whatever angle. Okay. But that would be a longitudinal.
Turned out.
Okay. So you have a compression and a distension, and sometimes it's called a pressure wave. And here's the density. So the graph that we would do, two chains.
These are rappers.
So we'd graph the density versus position of the spring below, and we would get the sine wave.
Ooh, another visual concept.
Okay, listen for this one.
As longitudinal waves move through a medium, they cause the particles of that medium to vibrate parallel to the direction in which the wave is moving. For example, a wave moving horizontally through a spring causes the atoms in the spring and anything attached to the coils to move back and forth.
How'd that thing go backwards? How did that happen? It was going
As
towards
longitudinal waves move through a medium, they cause the particles of that medium to vibrate parallel to the direction in which the wave is moving. For example, a wave moving horizontally through a spring causes the atoms in the spring and anything attached to the coils to move back and forth.
It's stretched out right before.
This, and then like this. Then it'll move this way. And then when the compression comes back, it'll move further.
An example of a longitudinal wave is sound. Sound is a longitudinal wave because all it is pressure. You're compressing the air that goes through your vocal cords. Use the definition of speed to determine the speed of a wave in terms of frequency and wavelength. What do you think it is? Sam, without looking. You guys remember from chemistry? What the speed of a wave in terms of frequency and wavelength? It's not anything to do with wavelength and speed. Okay, but then what? Distance is lambda, and then 1 over t is period, or the time is the period, and then so 1 over t is frequency. Right? So this was, so x, the distance for a wave, the distance is the wavelength. So we plug in lambda. Delta t, it's basically 1 over delta t times x, right? And 1 over delta t is equal to, or 1 over period is equal to frequency we had in the last section, right? So if we put 1 over our frequency in there, we'd have frequency times lambda is our equation for speed. And the speed, well, it depends on the medium. Speed of sound would be, or speed of light, I mean, is 3 times 10 to the 8th, which is what we used last year in chemistry. So the speed is constant for any given medium. So if frequency increases, then the wavelength has to decrease. They're inversely proportional. Wavelength is determined by the frequency and speed. So speed only changes if the medium changes. So hot air is different than cold air because the medium has changed. So the speed of sound is different and depending on the temperature of the air. Also depends on the gas. Different gases would have different speeds. Well, which molecules are moving faster in order to transfer the wave. Hot air it moves faster through. Would light gas or heavy gas move the?
Heavy.
Would make it faster?
You didn't let her finish the question, please.
Light gases. Light gases move faster than heavier gases.
But heavy gases are closer together, so they don't have to move fast.
More energy.
Not necessarily. They aren't necessarily closer together.
So if it was really humid air, it would move quickly. Okay, air would move slow.
Because water is heavier than a lot of the gases. Think about when you suck in helium. Your voice gets to be higher because the speed of sound in the helium that's in your lungs now moves faster than air normally does, and so that pitch is higher. If you have, I'll try to find the YouTube video of the guy. He sucks in, I think it's sulfur gas or something. It would make it really low. But it's denser than air, so it's hard to get out of your lungs and makes them almost puke. But because it's hard to get out of your lungs. I don't know why he did it.
Well, it sounded cool, I bet.
Yeah. Yep.
So, visual concept?
I don't know. Is that what's next?
Yeah.
Where's my?
Amplitude is the height of the wave. It is the maximum distance that the particles of a wave's medium vibrate from their rest position. Wavelength is the distance from any point on a wave to an identical point on the next wave. Period is the time it takes for a complete cycle or wave oscillation to occur. Frequency is the number of waves, cycles, or vibrations produced in a given unit of time.
All the way around, all right.
Wave speed is calculated by multiplying frequency by wavelength.
Okay.
Would you look at that? Did you just figure that out, Bunny?
You're about a couple months behind. That's not for sure. Last night I was like, oh.
Waves transfer energy from one point of the wave while the medium remains in place. So a diver loses his kinetic energy when it strikes the pool, water, but then the wave can carry that energy to the sides of the pool. That's one way that you can transfer energy because you don't have a net loss of energy, but it can get transferred. So that's one way it can get transferred. The energy depends on the amplitude. So higher amplitudes mean higher energy waves, and it's actually proportional to the square of the amplitude. So if the amplitude would be doubled, what factor does the energy increase? 4, because you read it on the slide. No. I say because you read it on the slide, or
No,
because it's squared.
something
Yeah.
about square.
Amplitude is squared, so the energy would be.
Square root of 2, you get a pretty number, so it has to be 4. Now what do we think?
So the size of the wave, how can we change the speed? Frequency or wavelength.
And both.
If the speed is constant, it depends on what you hold constant in that equation.
If your frequency stays constant, you change your wavelength.
Yeah.
Then you need a
Because the speed of a wave will change based on the medium, right? So that would be changing the material through which the wave is traveling. And then changing the frequency, that would change the speed. Right. Okay. I was going to... Yep, we're going to try it on page R.
Turn down to what? I'm just saying 2 from now on. Turn down to
I don't know if there would be one.
I figured you'd never get it. So, that was my
Yeah. There's not really a problem that to do over this. So we will do standing waves and we'll have problems over it tomorrow. Or not tomorrow. Yeah. Wednesday.